this video, I want to talk about material response to dynamic loads. Now, typically in an engineering dynamics course, we probably wouldn't cover material response to dynamic loads. However, I think it's important because we can start using it as a tool to think about, well, what are the applications of some of these things that we've done in dynamics and kind of our understanding of how dynamic behavior influences engineering design. So when we think about material response, probably the most relevant thing to dynamics from a materials perspective is how the material may respond to the rate at which some load is applied. And specifically, I'm thinking of viscoelasticity. So you may have heard of elastic materials, such as a spring or any sort of, for example, steel or something like that, which is going to behave in an elastic way as long as we keep the stresses relatively low. And when a material behaves elastically, it behaves like a spring. And what that means is that for any load that I put into that material, it's going to bounce back and I'll get recover that deformation that I've applied to the spring. You may also recall that we've previously talked about viscosity within the context of a dash pot. So a dash pot being a model of dampening in a system. And when we have a dash pot, one of the ways to create a dash pot is to put a fluid in a container and press it through some small holes such that the dash pot behaves in a rate-dependent manner, meaning that the faster I apply my load to my dash pot, the more resistance it's going to apply back at me to that motion. Whereas if I go slow, it won't resist very much. So viscoelasticity is basically the combination of those two things. And you're probably familiar with some viscoelastic materials, for example, silly putty. So I have a viscoelastic material here, very similar to silly putty. And if I take this material, you've probably seen things like this before, and I bounce it on a nice, thick, heavy textbook, it bounces away from me and ends up over on the floor. So this material is relatively elastic. Now, the reason that it bounced in that example is that I was applying a force relatively quickly to it. But of course, what you probably can predict already is that if I take this material and I pull it slowly, it stretches and behaves in a very different way. So depending on the rate at which I apply my force to this material, I get very different responses. And I can show this again, right? If I take this and I pull it slowly, it deforms, elongates, stretches like that. Now if I put my material back together and I pull it quickly, it fractures, right? And I get a very different response. It didn't stretch, it didn't elongate nearly as much, instead it broke. And so this type of strain rate dependent behavior is characteristic of viscoelastic materials that are exhibiting both elastic behavior and viscous behavior depending on the rate at which I apply my load and the different properties of my material. So we could model such a material using a combination of a spring and a dash pot, which kind of fits with the classic mass spring damper type system that we've looked at before. So in trying to understand viscoelastic materials and strain rate dependent behavior, we can get a better understanding of how materials might fail or not fail depending on the loads that we apply. And this is particularly important or relevant to areas and materials such as polymers or plastics, which exhibit this type of strain rate, many of which I should say, exhibit this type of strain rate dependent behavior. So if I apply the same load to a plastic slowly, it may not behave in the same way as if I were to apply that load quickly. And that could be important from an engineering design perspective. So we'll go into a little bit more detail on this in the next couple of videos, but I would just want to highlight the importance of strain rate dependent behavior for some materials. In terms of modeling viscoelastic material behavior in these types of materials, there's kind of two common models that we might look at just as examples. The first being a Maxwell model. And the Maxwell model basically assumes that we have a dash pot and a spring in series. Now, you might imagine, for example, one end of this model being fixed and the other having a load applied to it, for example. And of course, then under this model, we would have similar systems to what we've seen before, in that the damper has a dampening coefficient and the spring has a spring constant. However, typically when we're talking about material response, these models are given in terms of stress and strain. So force becomes stress, and spring constant becomes elastic modulus, and dampening coefficient becomes viscosity. Now, whether or not we're thinking about these in terms of stress or force doesn't really matter from this perspective. More or less what we're thinking is, how do we actually model this system, and what sort of response do we expect to get out of it? Another common model that's worth mentioning here is a Kelvin-Voigt model. And the slight difference between the Kelvin-Voigt model and the Maxwell model is that where the Maxwell model puts the spring and damper in series, the Kelvin-Voigt model puts them in parallel. So now the system looks like this from a modeling perspective, and we can think about it kind of in the same way. Now, for a class in dynamics, we're not going to get into very deeply at all how to actually apply these models, but I'm sure that they look familiar, right? Especially the Kelvin-Voigt model looks very similar to a standard mass spring damper system, where we saw that we got a second order differential equation that allowed us to analyze the dynamics of that situation. And we could apply the same sort of principles using this model when we're talking about material response. Now, which model of these two, for example, you might choose, or one of the others that are out there, kind of depends on what material you would be talking about. So different polymers might fit better within one of these different models, and different loading scenarios might be handled better by one of these models versus the other. Now, which one you choose, to approximate your system would come with experience, and would come with maybe an experimental understanding of the material behavior and what you might expect to get out of it. So from the perspective of engineering dynamics and a class in dynamics, I just wanted to point out that these models exist, and that there are ways that we can model the dynamic behavior of materials in the same way that we might model the dynamic behavior of rigid systems, due to the mass of the objects. In this case, we're actually talking about the deformation of the material itself. Thanks.